Hello and good afternoon to the Science Museum on an incredibly auspicious day as the launch of the Collider exhibition. And the reference to going live was that we are live streaming this event on theguardian.com as part of our media partnership with the Science Museum. I'm editor of The Observer, and I'm incredibly pleased that our parent group, Guardian News Media, is a media partner not only for this Collider exhibition, but also for the series of events which will mark the exhibition's 6-month residency here. And the first of those is, of course, today. So you can go online if you're perhaps at the back blogging and see what the instant reaction is. The reason I'm incredibly pleased that the Observer and Guardian are part of this incredible event is that since the Observer was first founded in 1791, and it's the oldest Sunday newspaper in the world, science has always been one of the building blocks, part of the paper's DNA. And the same is true of the Guardian. And it's one of the reasons why a couple of months ago we launched a new supplement called Observer Tech Monthly. But it is in fact a supplement devoted to technology, science, and ideas. And I hope that most recent initiative links back to the birth of the paper's commitment to science at a time, not necessarily in Britain, but certainly in other parts of the world, where science is under some assault, and particularly at a time when science is perhaps the best navigating tool we have through issues such as new areas of medicine and climate science and such like. So we're going to hear a great deal more about the exhibition and the motives and insights behind it. But one of the other points I wanted to make was that science and culture is the other part of what brings the Observer to this exhibition. And as Roger Highfield, who's the head of external comms at the Science Museum, mentions in an interview in the Evening Standard today, those two disciplines are really not so very far apart, although some people like to position them at polar opposites. But it's of course true that artists have often been guided by rigor, and some scientists guided by intuition and insight, and vice versa. And what better way for those two worlds to come together than in the conversation we're going to hear in 45 minutes, when one of our greatest novelists, Ian McEwan, will speak with leading theoretical physicist Nima Arkham Hamad, and those two worlds will, if not collide, certainly come together. But before then, I want you to put your hands together for the person who was instrumental in literally bringing the Collider experience to the Science Museum, and that's the curator of astronomy and physics at the Science Museum, Alison Boyle.
Thank you, John. It's been a very exciting day so far for us. It's been a real privilege to have so many people from the world of particle physics and CERN here today to see how we've brought the Collider to life. As John mentioned, I'm the museum's curator of astronomy and physics, so that makes it a particular honour to introduce our next speaker. His groundbreaking research in cosmology has earned many awards, including recently the Fundamental Physics Prize. Popularising his research for a wide audience has made him a household name. There certainly aren't many scientists who could claim to have been immortalised as a Simpsons action figure. And the physical constraints he has overcome have made these achievements all the more remarkable. Ladies and gentlemen, could you please welcome Professor Stephen Hawking to the stage?
Before we begin this journey into space and time, I would like to thank the Science Museum, which is one of my favorite places. I have been coming here for decades. And that simple fact, in itself, tells quite a story. When I was 71 earlier this year, I became the longest known survivor with ALS, a condition that I was diagnosed with in my 20s. Last year, the museum put on a special display to celebrate my 70th. It was a remarkable moment when I came to see it, and hundreds of people sang happy birthday to me. I was given this present by the museum, a black hole light, which consists of illuminated spirals to symbolize a black hole and Hawking radiation, a reference to my prediction that black holes will give off radiation. I'll talk about that later. The museum put me in touch again with David Hockney. Hockney had drawn a portrait of me once before, in 1978, when he produced several line drawings. This time he produced an iPad portrait. I am still not quite sure about the fingers. Throughout my life, I have had a gambling problem. When I was 12, one of my friends bet another friend a bag of sweets that I would never come to anything. I don't know if this bet was ever settled, and if so, which way it was decided. I had 6 or 7 close friends, and we used to have long discussions and arguments about everything, from radio-controlled models to religion. One of the things we talked about was the origin of the universe, and whether it required a god to create it, and set it going. I had heard that light from distant galaxies was shifted towards the red end of the spectrum, and this was supposed to indicate that the universe was expanding. But I was sure there must be some other reason for the red shift. Maybe light got tired, and more red, on its way to us. An essentially unchanging and everlasting universe seemed so much more natural. It was only after the discovery of the cosmic microwave background, about 2 years into my PhD research, that I realized I had been wrong. When I came to the last 2 years of school, I wanted to specialize in mathematics and physics, because I thought this was the most fundamental science. Physics and astronomy offered the hope of understanding where we came from, and why we were here. My father was also very keen, that I should go to Oxford or Cambridge. He himself had gone to University College, Oxford, so he thought I should apply there. But at that time, University College had no fellow in mathematics, so I had little option but to try for a scholarship in natural science. I surprised myself by being successful. In the end, I have wound up being a professor of mathematics, but I have not had any formal instruction in mathematics since I left school at the age of 17. I have had to pick up what mathematics I know as I went along. When I used to supervise maths undergraduates, I would keep 1 week ahead of them in the course. At Oxford, the physics course was arranged in a way that made it particularly easy to avoid work. I did 1 exam before I went up, then had 3 years at Oxford, with just the final exams at the end. I once calculated that I did about 1,000 hours work in the 3 years I was there, an average of an hour a day. I'm not proud of this, I'm just describing my attitude at the time, shared by most of my fellow students. Because of my lack of work, I had planned to get through the final exam by doing problems in theoretical physics and avoiding questions that required factual knowledge. But I didn't sleep the night before the exam because of nervous tension, and so I didn't do very well. I was on the borderline between a first and second class degree, and I had to be interviewed by the examiners to determine which I should get. In the interview they asked me about my future plans. I replied that I wanted to do research. If they gave me a first, I would go to Cambridge. If I only got a second, I would stay in Oxford. They gave me a first. I was 20 in October 1962 when I arrived in Cambridge at DAMTP, the Department of Applied Mathematics and Theoretical Physics. I had applied to work with Fred Hoyle, the most famous British astronomer of the time. I say astronomer because cosmology then was hardly recognized as a legitimate field. However, Hoyle had enough students already, so to my great disappointment, I was assigned to Dennis Sharma, of whom I had not heard. But it was just as well I hadn't been a student of Hoyle, because I would have been drawn into defending his steady-state theory, a task which would have been harder than saving the euro. I hadn't done much mathematics in the very easy physics course at Oxford, so Sharma suggested I work on astrophysics. But having been cheated out of working with Hoyle, I wasn't going to do something boring. I had come to Cambridge to do cosmology, and cosmology I was determined to do. At that time, cosmology and gravitation were neglected fields that were ripe for development. So I read old textbooks on general relativity and traveled up to hear relativity lectures at King's College, London each week. I followed the words and equations, but I didn't really get a good feel for the subject. At that time, it became clear something was not quite right with me. Already in Oxford, I had noticed that I could no longer row a sculling boat properly. The Christmas after arriving in Cambridge, I went home. It was a very cold winter and my mother persuaded me to go skating on the lake in St. Albans, even though I knew I was not up to it. I fell over and had great difficulty getting up again. There didn't seem any point working on my PhD, because I didn't know if I would live long enough to finish it. But then the condition developed more slowly, and I began to make progress in my work. After my expectations had been reduced to zero, every new day became a bonus, and I began to appreciate everything I did have. While there's life, there is hope. And there was also a young woman called Jane, whom I had met at a party. Getting engaged lifted my spirits, and I realized, if we were going to get married, I had to get a job and finish my PhD. I began to work hard, and I enjoyed it. The big question in cosmology in the early 60s was, did the universe have a beginning? Many scientists were instinctively opposed to the idea, because they felt that a point of creation would be a place where science broke down. One would have to appeal to religion and the hand of God to determine how the universe would start off. Two alternative scenarios were therefore put forward. One was a steady-state theory, in which as the universe always expanded, a new matter was continually created to keep the density constant on average. By the time I began my research, the steady-state theory was already in trouble with observations, but the final nail in the coffin came with the discovery of a faint background of microwave radiation in 1964. The only reasonable interpretation of the background is that it is radiation left over from an early very hot and dense state. As the universe expanded, the radiation would have cooled until it is just the faint remnant we observe today. But there was a second alternative to a beginning in time, which is a bouncing, or even cyclic universe. Perhaps the universe had a previous contracting phase, and that it had bounced from contraction to expansion, at a high, but finite density. This was clearly a fundamental question, and it was just what I needed to complete my PhD thesis. Two Soviet scientists, Lifshitz and Kalatnikov, had claimed to have proved that contraction in general relativity without any special symmetry would always lead to a bounce, with the density remaining finite. This result was very convenient for Marxist materialism, because it avoided awkward questions about the creation of the universe. Lifshitz and Kalatnikov were members of the old school in general relativity. That is, they wrote down a massive system of equations and tried to guess a solution. But it wasn't clear that the solution they found was the most general one. A new approach was introduced by Roger Penrose, which didn't require solving the field equations explicitly, just certain general properties, such as that energy is positive and gravity is attractive. Penrose had showed that once a dying star had contracted to a certain radius, there would inevitably be a singularity, a point where space and time came to an end. I realized that similar arguments could be applied to the expansion of the universe. In this case, I could prove there were singularities where spacetime had a beginning. So Lifshitz and Kalatnikov were wrong. General relativity predicted that the universe should have a beginning. Up to 1970, my main research interest was in the Big Bang singularity of cosmology, rather than the singularities or black holes that Penrose had shown would occur in collapsing stars. My work on black holes began with the eureka moment, a few days after the birth of my daughter, Lucy. While getting into bed, I realized that I could apply to black holes the causal structure theory I had developed for singularity theorems. In particular, the area of the horizon, the boundary of the black hole, would always increase. When two black holes collide and merge, the area of the final black hole is greater than the sum of the areas of the original holes. This suggested that the area of a black hole was like what is called the entropy in thermodynamics. It would be a measure of how many states a black hole could have on the inside for the same appearance on the outside. But the area couldn't actually be the entropy, because as everyone thought they knew, black holes were completely black and couldn't be in equilibrium with thermal radiation. There was a golden age in which we solved most of the major problems in black hole theory. This was before there was any observational evidence for black holes. In fact, we were so successful with the classical general theory of relativity that I was at a bit of a loose end in 1973 after the publication with George Ellis of our book, The Large-Scale Structure of Spacetime. My work with Penrose had shown that general relativity broke down at singularities. So the obvious next step would be to combine general relativity, the theory of the very large, with quantum theory, the theory of the very small. I had no background in quantum theory, and the singularity problem seemed too difficult for a frontal assault at that time. So as a warm-up exercise, I considered how particles and fields governed by quantum theory would behave near a black hole. In particular, I wondered, can one have atoms in which the nucleus is a tiny primordial black hole formed in the early universe? To answer this, I studied how quantum fields or particles would scatter off a black hole. I was expecting that part of an incident wave would be absorbed, and the remainder scattered. But to my great surprise, I found there seemed to be emission from the black hole. At first, I thought this must be a mistake in my calculation. But what persuaded me that it was real was that the emission was exactly what was required to identify the area of the horizon with the entropy of a black hole. It is summed up in this simple formula, which expresses the entropy in terms of the area of the horizon and the three fundamental constants of nature: c, the speed of light; g, Newton's constant of gravitation; and h bar, Planck's constant. I am proud to have discovered it. I would like this equation to be on my memorial, like Boltzmann and his formula for entropy. Later work uncovered the deep reason for this formula. General relativity can be combined with quantum theory in an elegant manner if one replaces ordinary time by imaginary time. This is called the Euclidean Approach because it makes time become a fourth direction of space. The Euclidean space-time is smooth, and contains no singularity at which the equations of physics could not be defined. It solved the fundamental problem that the singularity theorems of Penrose and myself had raised, that predictability would break down because of the singularity. The radiation from a black hole will carry away energy, so the black hole will lose mass and shrink. Eventually, it seems the black hole will evaporate completely and disappear. This raised a problem that struck at the heart of physics. My calculation showed that the radiation was exactly thermal and random, as it has to be, if the area of the horizon is to be the entropy of the black hole. So how could the radiation left over carry all the information about what made the black hole? But if information is lost, this is incompatible with quantum mechanics. This paradox had been argued for 30 years, without much progress, which is what often happens in research. But if you get stuck, it's no good getting furious. You just have to keep thinking about the problem while working on something else. Eventually, I found what I think is its resolution. Information is not lost in black holes, but it is not returned in a useful way. It is like burning an encyclopedia. Information is not lost, but it is very hard to read. In fact, Kip Thorne and I had a bet with John Preskill on the information paradox. I gave John a baseball encyclopedia. Maybe I should have just given him the ashes. The fact that I used to think that information was destroyed in black holes was my biggest blunder. Well, at least it was my biggest blunder in science. During the 1970s, I had been working mainly on black holes. But my interest in cosmology was renewed by the suggestions that the early universe had gone through a period of inflationary expansion, in which its size grew at an ever-increasing rate, like the way prices go up in the shops. In early 1982, I wrote a preprint proposing that the seeds for structures in our universe could be created by quantum effects during inflation. This was basically the same mechanism as radiation from a black hole horizon, except that this time it came from the cosmological horizon. I had used Euclidean methods earlier with Gary Gibbons to work out the temperature of de Sitter space. We held a Nuffield workshop in Cambridge that summer, attended by all the major players in the field. At this meeting, we established most of our present picture of inflation, including the all-important density fluctuations, which give rise to galaxy formation, and so to our existence. Several people contributed to the final answer. This was 10 years before fluctuations in the microwave sky were discovered by the Kobe satellite in 1993, so theory was way ahead of experiment. Cosmology became a precision science another 10 years later, in 2003, with the first results from the WMAP satellite. WMAP produced a wonderful map of the temperature of the cosmic microwave sky, a snapshot of the universe at about 1/100th of its present age. The irregularities you see are predicted by inflation, and they mean that some regions of the universe had a slightly higher density than others. The gravitational attraction of the extra density slows the expansion of that region, and can eventually cause it to collapse to form galaxies and stars. So look carefully at the map of the microwave sky. It is a blueprint for all the structure in the universe. Superseding WMAP, today there is a Planck satellite, with a much higher resolution map of the universe you see here on stage, released last month. Planck will test our theories in earnest, and may even detect the imprint of gravitational waves predicted by inflation. This would be quantum gravity written across the sky. The original scenario for inflation was that the universe began with a Big Bang singularity. As the universe expanded, it was supposed somehow to get into an inflationary state, but I thought this was unsatisfactory. Unless one knew what came out of the initial singularity, one could not calculate how the universe would develop. Cosmology would not have any predictive power. What was needed was a space-time without singularity, like in the Euclidean version of a black hole. After the 1982 workshop in Cambridge, I spent time at the Institute of Theoretical Physics in Santa Barbara. I talked to Jim Hartle about how to apply the Euclidean approach to cosmology. According to this approach, the quantum wave function of the whole universe is given by a Feynman sum over a certain class of histories in imaginary time. Because imaginary time behaves like another direction in space, Histories in imaginary time can be closed surfaces, like the surface of the Earth, with no beginning or end. Jim and I concluded that this was the only natural choice. We formulated the no-boundary proposal. The boundary condition of the universe is that it has no boundary. We had sidestepped the scientific and philosophical difficulty of time having a beginning by turning it into a direction in space. In this picture, the universe will be spontaneously created out of nothing. It will start out almost completely smooth, except for the tiny departures predicted by inflation, which then give rise to all the structure in the universe we see about us. Around the time of my no-boundary work, I decided to write a popular book. I thought I might make a modest amount to help support my children at school and the rising costs of my care, but the main reason was because I enjoyed it. While I was writing it, I visited CERN and I became critically ill with pneumonia and lost my voice due to a tracheostomy. But I kept putting a lot of effort into the book, because I think it's important for scientists to explain their work, particularly in cosmology. I never expected a brief history of time to do as well as it did. Not everyone may have finished it, or understood everything they read. But they at least got the idea that we live in a universe governed by rational laws that we can discover and understand. More recently, I wrote a new book, The Grand Design, with Leonard Mlodinov, to try to address a few issues left unresolved in a brief history. You see, the laws of science describe how the universe behaves, but to understand the universe at the deepest level, we also need to understand why. Why is there something rather than nothing? Why do we exist? Why this particular set of laws, and not some other? I believe the answer to all these questions is M theory. M theory is the only unified theory which has all the properties that we think the final theory ought to have. It is not a theory in the usual sense, but it is a whole family of different theories, each of which is a good description of observations only in some range of physical situations. M theory predicts that a great many universes were created out of nothing. These multiple universes can arise naturally from physical law. Each universe has many possible histories and many possible states at later times, that is, at times like the present, long after their creation. Most of these states will be quite unlike the universe we observe, and quite unsuitable for the existence of any form of life. Only a very few would allow creatures, like us, to exist. Thus our presence selects out from this vast array only those universes that are compatible with our existence. Although we are puny and insignificant on the scale of the cosmos, this makes us in a sense, lords of creation. There is still hope that we see the first evidence for M-theory at the Lhc Particle Accelerator in Geneva. When the LHC started up in September 2008, people worried that it might create a world-eating black hole. Personally, I wouldn't have even bet a penny on it. But even if the LHC had made a black hole, it would have evaporated via Hawking radiation before it could do any harm. So the fate of the world relied on me being right. From an M-theory perspective, the collider only probes low energies, but we might be lucky and see a weaker signal of fundamental theory, such as supersymmetry. I think the discovery of supersymmetric partners for the known particles would revolutionize our understanding of the universe. I don't feel the same way about the Higgs boson. Physics would be far more interesting if it had not been found. A few weeks ago, Peter Higgs and Francois Englert shared the Nobel Prize for their work on the boson, and they richly deserved it. Congratulations to them both. But the discovery of the new particle came at a personal cost. I had a bet with Gordon Kane of Michigan University that the Higgs particle wouldn't be found. The Nobel Prize cost me $100. The beginning of the universe itself in the hot Big Bang is the ultimate high-energy laboratory for testing M-theory and our ideas about the building blocks of space-time and matter. Different theories leave behind different fingerprints in the current structure of the universe, so astrophysical data can give us clues about the unification of all the forces of nature. There are many ambitious experiments planned beyond Planck. We will map the positions of billions of galaxies, and with the help of supercomputers like Cosmos, we will better understand our place in the universe. Perhaps one day, we will be able to use gravitational waves to look right back into the heart of the Big Bang. Most recent advances in cosmology have been achieved from space, where there are uninterrupted views of our vast and beautiful universe. But we must also continue to go into space for the future of humanity. I don't think we will survive another 1,000 years without escaping beyond our fragile planet. I therefore want to encourage public interest in space, and I've been getting my training in early. So let me finish by reflecting on the state of the universe. The latest Nobel is another reminder that this is a glorious time to be alive and doing research in theoretical physics. Our picture of the universe has changed a great deal in the last 50 years, and I'm happy if I have made a small contribution. The fact that we humans, who are ourselves mere collections of fundamental particles of nature, have been able to come this close to an understanding of the laws governing us and our universe is a great triumph. I want to share my excitement and enthusiasm about this quest. So remember to look up at the stars and not down at your feet. Try to make sense of what you see and hold on to that childlike wonder about what makes the universe exist. I also hope that the Science Museum's smashing new Collider exhibition will help satisfy our boundless curiosity about our place in the universe. Thank you for listening.
The Collider exhibition is a journey inside the greatest experiment on Earth, the Large Hadron Collider at CERN. And because not everyone can go to CERN, we thought that we would bring CERN to London. Laurie arrived from CERN a couple of hours ago, and we have 5 tons of CERN going on to gallery today, which is simultaneously exciting and terrifying. We've been lucky enough over the years to go to CERN, and it's been an incredible experience to see the scale of the place and meet the people there and hear the passion that they have for their work, and it was something that we really wanted to bring to our visitors. The Large Hadron Collider is a pretty tricky subject for a museum. Most of the Large Hadron Collider is far bigger than the Science Museum. The accelerator ring itself is 27 kilometres around, so that is the same size as the Circle Line. At the other end of the scale, what they're looking for are invisible particles. And right from the start we thought, actually the way to do that is to work with people who work in theatre, because theatre transports you to other worlds.
So the whole exhibition is set up as a visit to CERN. You'll be walking into reconstructed spaces of real places at CERN where you'll see the objects set in context, and there will be projections of scientists and engineers talking to you about their work and about life at CERN.
We've worked with such a different and creative, fantastic team to build this whole thing together. It's not quite an exhibition, it's not quite a piece of theatre, it is something that blends both.
I think it's hard not to be amazed by the ambition of what's being done at CERN. The LHC is an amazing machine. Everything about it is kind of extreme or pushing the limits of what's possible. And all of this just to find out more about the world we live in. And that's what's exciting about it. Potentially what we find out at the LHC could completely change the way we think about the universe.
It is the greatest experimental endeavour in science. Although there's been quite a lot in the news recently about the Higgs boson, that is just the beginning of the LHC's journey. The LHC was designed and built to answer a lot of fundamental questions about the universe. It's about the value of pure human curiosity, and I think that's something that can inspire everybody.